Everything that has ever fallen into a black hole still exists, not as dust, not as memory, not as energy scattered into darkness. Every star that was swallowed, every planet that was pulled apart, every photon of light that crossed the edge of no return, it still exists, somewhere, in some form that our physics cannot yet name or locate. The universe kept a receipt for every one of them. That is not a philosophical suggestion. That is, to the best of our current scientific understanding, a statement of fact. Picture this. High desert in Chile, 4 kilometers above sea level, 2 in the morning, in the winter of 2019. The air is so dry it crackles faintly when you breathe. A technician named Cristina Romero is walking between 2 domed telescope buildings, her breath turning white in the cold. She is not rushing. She's walked this path 1,000 times. Above her, the Milky Way is so dense and so sharp it looks close enough to touch, not the soft smear most people see from cities, but a solid, 3-dimensional structure of light and dust and gas that gives the real impression of depth, of distance, of something so vast that the word vast immediately fails. She stops, she looks up, and she feels it. The thing that everyone who works here eventually feels, which is not wonder exactly, but the specific vertigo of being a creature with a 70-year lifespan staring at processes that have been running for 14 billion years. She is about to run a calibration check on data collected by the Event Horizon Telescope, a network of radio observatories strung across the Earth, working in concert to form a single instrument the size of the planet. That instrument has just photographed something that was thought, for most of human history, to be impossible to see: the boundary of a black hole, the edge past which nothing returns, the threshold, the horizon. For 60 years, black holes were theoretical objects, mathematical solutions to Einstein's equations that physicists largely assumed nature would never actually build. Too extreme, too strange. Then we found one. Then we found millions. Then we found that every large galaxy, including ours, has a black hole at its center with a mass of millions or billions of suns. Then we found that black holes don't just sit there, they shape everything around them. They drive the formation of galaxies. They regulate starbirth. They are, in a very real sense, the architects of the visible universe. And then we ran into a problem. Not a small problem, not a problem at the edge of our measurements that might dissolve with better instruments. A problem that sits at the absolute center of our 2 most successful theories of how reality works and tears them apart. The problem is this: everything we know about quantum mechanics, the theory that governs the behavior of particles at the smallest scales, the theory that gave us computers, lasers, and MRI machines, the most precisely tested theory in the history of science, tells us that information can never be truly destroyed. Scrambled, yes. Dispersed, yes. But destroyed, impossible. The laws of quantum mechanics forbid it, the way the laws of arithmetic forbid dividing by 0. It is not just a rule, it is the foundation the whole structure rests on. Black holes, according to everything we know about gravity and spacetime, destroy information completely. These 2 things cannot both be true, and yet both appear to be true, and no one, not a single physicist alive, can tell you how to resolve that without demolishing something essential about the way we understand reality. Here is the question that sits at the heart of this documentary. The question that has consumed some of the most brilliant minds in theoretical physics for 50 years, and that still does not have a settled answer. What actually happens to something when it falls into a black hole? Not what happens to the matter, not what happens to the energy. What happens to the information, the precise quantum state of every particle, the complete description of everything that thing ever was? Does it survive? Is it hidden somewhere we cannot see? Does it leak out in a form we cannot yet decode? Or is it simply gone? And if it is gone, does that mean that one of our 2 great theories of reality has been wrong all along, in some deep and fundamental way that we have not yet identified? By the time this script ends, you will understand not just what black holes are, but what they reveal about the nature of space, time, information, and the structure of reality itself. You will understand why the world's leading physicists are not just puzzled by black holes, they are shaken by them. You will understand why the answer to what lies beyond the black hole horizon might be the most consequential scientific discovery in the history of human thought. and you will leave with a question you will not be able to stop thinking about. The man who first understood what black holes really were did not call them black holes. He called them Schwarzschild singularities, and he was working in a trench. His name was Karl Schwarzschild. He was a German physicist, and in 1915, while Einstein was publishing his general theory of relativity, the theory that replaced Newton's gravity with a description of spacetime itself curving and bending in response to mass, Schwarzschild was serving as an artillery officer on the Eastern Front of the First World War. He was 42 years old, brilliant, meticulous, and apparently capable of doing field-redefining theoretical physics between artillery calculations. Within weeks of Einstein publishing his equations, Schwarzschild found an exact solution to them. Not an approximation, an exact solution for the special case of the gravitational field around a perfectly spherical, non-rotating mass. He mailed it to Einstein from the trenches. Einstein wrote back that he was astonished. The solution contained something disturbing, had a specific radius around any sufficiently compressed mass, a radius now called the Schwarzschild radius. The mathematics became singular. It broke. Coordinates went to infinity. Equations that should describe smooth, continuous spacetime suddenly described something that appeared to be a physical surface, a boundary around a compressed mass at which the geometry of space itself became so severely curved that escape became impossible. Light could not get out. Matter could not get out. Causality itself, the chain of cause and effect that connects all events in the universe, appeared to terminate at this surface. Schwarzschild never saw what his equation meant in full. He died in May 1916 on the Eastern Front from a skin disease contracted at the front. He was 42. His discovery sat in the literature for decades, treated mostly as a mathematical curiosity, a technically valid solution to Einstein's equations that nature would presumably never actually produce. The assumption that nature would not produce black holes began to crack in the 1930s. Subrahmanyan Chandrasekhar, a 20-year-old Indian physicist making the sea voyage from Madras to Cambridge, spent the weeks on the ship calculating what would happen to a massive star when it exhausted its nuclear fuel. His answer, worked out with a pencil in a ship's cabin in the middle of the ocean, was this: stars above a certain mass, approximately 1.4 times the mass of the Sun, a threshold now called the Chandrasekhar limit, could not stop collapsing. There was no physical mechanism that could halt their implosion. They would compress past the Schwarzschild radius. They would become the thing Schwarzschild's equations described. When Chandrasekhar presented this finding at the Royal Astronomical Society in 1935, Arthur Eddington, the most respected astrophysicist in Britain, publicly dismissed it. Standing at the lectern, Eddington announced that nature would surely have some way to prevent stars from collapsing to a singularity, because the alternative was too absurd. He did not offer a mechanism, he offered an aesthetic objection. Chandrasekhar was right, Eddington was wrong, but it would take another 3 decades for the evidence to become undeniable, and it would arrive from a direction no one was looking. In the 1960s, astronomers began cataloguing powerful radio sources in the sky, objects that emitted enormous amounts of energy across the electromagnetic spectrum, far more than any star or galaxy they had previously measured. When Martin Schmidt at the California Institute of Technology calculated the distance to one of these objects in 1963, a point source catalogued as 3C273, he found that it was 3 billion light-years away and yet bright enough to be visible from Earth. That meant it was emitting more energy than an entire galaxy of hundreds of billions of stars, all packed into a region no larger than the solar system. These objects were called quasars, quasi-stellar radio sources. And the only mechanism that could explain their energy output, after years of searching for alternatives, was gravitational, specifically matter falling into an extremely compressed mass, a mass of millions or billions of suns, losing gravitational potential energy as it spiraled inward, heating up to billions of degrees and emitting light across every wavelength. The compressed mass at the center had to be what Schwarzschild's equations described. Had to be. The term black hole was coined, or at least popularized, by the physicist John Archibald Wheeler in 1967. During a lecture at NASA's Goddard Institute, Wheeler was one of the great science communicators of the 20th century. A man who had worked on the Manhattan Project, had been a student of Niels Bohr. and who had a gift for language that matched his gift for mathematics. The phrase caught. It spread. It replaced the dry terminology, gravitationally collapsed object, frozen star, with something visceral and immediate. And then in 1974, Stephen Hawking did something that changed the problem entirely. He calculated what happened when quantum mechanics was applied to the region just outside a black hole's event horizon. And what he found was not a curiosity, it was a catastrophe. Hawking showed that black holes are not black. They glow. They radiate energy faintly at a temperature inversely proportional to their mass in a process now called Hawking radiation. A stellar mass black hole radiates at a temperature so close to absolute zero that the radiation is currently undetectable. But the math is unambiguous. Black holes lose energy, and if they lose energy, they lose mass. And if they lose mass continuously, they eventually evaporate completely. When a black hole evaporates, what happens to the information that fell in? That question, Hawking's question asked first in 1975, is the crack in the foundations. And 50 years later, that crack has not closed. It has widened. The information paradox is not one anomaly. It is 4 interlocking anomalies, each one disturbing on its own, each one worse when seen alongside the others. The first anomaly is the most basic. In quantum mechanics, every physical system has a mathematical description called a quantum state, a complete specification of all the information the system contains. When a physical process occurs, when particles interact, when energy is exchanged, when any physical change happens, the quantum state evolves. Crucially, it evolves in a way that is reversible. Given the output state, you can, in principle, calculate the input state. The equations of quantum mechanics are time-symmetric. Information is preserved, always. This is not just a technical rule. It is the reason the universe has memory. It is the reason that events can be caused by previous events. It is the reason that physics, the enterprise of understanding the rules of the universe, is possible at all. If information could be destroyed, then the universe's past would not uniquely determine its future. Physics would be, at its foundations, incoherent. Now consider what happens when a book falls into a black hole. The quantum state of the book, the precise arrangement of every atom, every electron's spin, every photon that ever interacted with its pages, is information, complex, enormous in quantity, but finite. According to quantum mechanics, that information cannot be destroyed. According to general relativity, Einstein's theory of gravity tested to extraordinary precision across more than a century, what happens when the book crosses the event horizon is this: nothing special. The event horizon is not a physical surface. It is not a wall. It is not a place where matter is compressed or heated or torn apart. It is a mathematical boundary, a line of no return, defined not by any local physical condition, but purely by the causal structure of spacetime. A physicist in freefall crossing an event horizon would feel nothing unusual at the moment of crossing. No jolt, no burning, no signal that the threshold had been passed. They would simply be inside. They simply could not leave. But then Hawking radiation enters. Hawking showed that the thermal radiation emitted by a black hole carries no information. It is purely random, a featureless bath of thermal photons, carrying no imprint of the quantum states that formed the black hole or fell into it. If the black hole eventually evaporates completely, and the radiation that remains carries no information, then the information is gone, destroyed. The universe has, in an important physical sense, forgotten. This is the first anomaly. The mathematics of quantum mechanics and the mathematics of general relativity make directly contradictory predictions about what happens to information at a black hole. The second anomaly is subtler and in some ways more disturbing. It concerns the experience of different observers and reveals that the contradiction is not just about what happens, but about where reality happens. Consider two physicists. One, call her Alice, is in freefall, crossing the event horizon of a large black hole. The other, call him Bob, is hovering at a safe distance, watching Alice fall, according to Alice's experience, and according to general relativity's principle that free-falling observers experience smooth, undisturbed spacetime. She crosses the horizon without incident. She continues inward. She eventually encounters the singularity at the black hole's center. Nothing unusual marks her passage through the horizon, according to Bob's experience. However, And according to the equations of quantum mechanics applied to the region just outside the horizon, the radiation that Hawking showed must be emitted from the horizon region comes from quantum fluctuations in the vacuum near the horizon. These fluctuations involve pairs of entangled virtual particles. One falls in, one escapes. The escaped particle is the Hawking radiation, and crucially, this process, considered carefully, means that the information in the infalling material must somehow be encoded in the outgoing radiation if it is to survive. In 2012, physicists Ahmed Almheri, Donald Maroff, Joseph Polchinski, and James Sully, working at the University of California, Santa Barbara, published a paper that took this contradiction to its logical conclusion and found something horrifying. They showed that if you require three things simultaneously, that information is preserved, that quantum mechanics worked normally far from the horizon, and that an infalling observer experiences nothing unusual at the horizon, you arrive at a mathematical contradiction. These three requirements cannot all be true at once. They call the implication a firewall. If information must survive, and if quantum mechanics must work correctly far from the black hole, then something must destroy the information before it crosses the horizon. That something would appear to an infalling observer as an infinitely energetic barrier. A wall of fire at the horizon that would incinerate anything approaching. This is the second anomaly. The three most basic requirements we would ask of a physical theory: preserve information, respect quantum mechanics, respect the equivalence principle of general relativity, cannot simultaneously be satisfied at a black hole horizon. Almheri, Maroff, Polchinski, and Sully had not solved the paradox. They had sharpened it into a knife. The third anomaly concerns entanglement, and it cuts even deeper. In quantum mechanics, entanglement is the phenomenon whereby two particles share a quantum state. Measuring one instantly determines a property of the other, regardless of the distance between them. Einstein called it spooky action at a distance and spent years trying to prove it was not real. Every experiment confirms it is real. In 2013, Juan Maldacena at the Institute for Advanced Study in Princeton and Leonard Susskind at Stanford University published a remarkable paper whose title was, with deliberate provocativeness, Cool Horizons for Entangled Black Holes. Their central claim, that entanglement and space-time geometry are not just analogous, they may be the same thing: a wormhole, a tunnel through space-time connecting two distant regions, and the pair of entangled particles may be two descriptions of the same physical reality. The equation at the paper's heart, written ER equals EPR, linked Einstein-Rosen Bridges, wormholes, which Einstein and Nathan Rosen described in 1935, with Einstein-Podolsky-Rosen pairs, entangled particles, which Einstein and colleagues described in the same year. Two papers from 1935, never connected, might be describing the same phenomenon at different scales. This is the third anomaly, and the most extraordinary. If space-time itself is built from entanglement, then the destruction of entanglement at a black hole horizon is not just an information problem. It is a geometry problem. Destroying the entanglement might, in some technical sense, destroy the fabric of space-time itself. The fourth anomaly is perhaps the most quietly disturbing because it does not come from a sophisticated calculation, it comes from counting. Jacob Bekenstein, a graduate student working under John Wheeler at Princeton in the early 1970s, proposed a startling conjecture that a black hole has entropy, thermodynamic entropy, the measure of a number of possible internal states of a system, and that this entropy is proportional not to its volume, as you would expect for any other physical object, but to the area of its event horizon. Stephen Hawking confirmed this mathematically in 1973. The entropy of a black hole goes as area, not volume. This is the Bekenstein-Hawking entropy. Why is this disturbing? Because it suggests that the information content of the three-dimensional interior of a black hole is fully described by a two-dimensional surface, as if the volume inside has no independent reality, as if it is a projection, a hologram, of information written on the surface. That is not an analogy, the mathematics requires it, and no one fully understands what it means. Before the three revelations that follow, we need to build the floor beneath your feet, because the concepts that collide inside a black hole are not intuitive. They have to be constructed carefully, one idea at a time, until the collision becomes visible. Start with space-time. Before Einstein, space and time were separate things. Space was the three-dimensional stage on which events happened, and time was the universal clock ticking the same rate everywhere. Einstein's special relativity showed this was wrong. Space and time are not separate. They are woven into a single four-dimensional fabric called spacetime. An event does not happen at a place and a time. It happens at a location in spacetime. And crucially, different observers, moving at different speeds, measure time and space differently. What looks like pure time to one observer looks like a mixture of time and space to another. The fabric is real, and it stretches. Think of it like this. You are standing still on a train platform, watching a train go by. The train is moving in space. It travels along the platform in one direction. But imagine that every physical object has a fixed total velocity through space-time, through both space and time together, and that this velocity is always equal to the speed of light. When the train moves through space, it is spending some of its space-time velocity on the spatial dimension, and therefore it moves more slowly through time. The clock on the moving train runs slower than the clock on the platform. This is not an illusion. It has been measured with atomic clocks on airplanes. The analogy holds precisely for the intuition, though the full mathematics is richer. General relativity extends this. It says that mass and energy tell space-time how to curve. A heavy object, a star, a planet, a galaxy, dents the fabric of space-time the way a bowling ball dents a rubber sheet. Other objects moving through that curved space-time follow curved paths, what we experience as gravity. The rubber sheet analogy is useful but has a well-known failure. Rubber sheets are two-dimensional, and the curvature of space-time is four-dimensional and involves time as well as space. The key difference is this: it is the curvature of time near a massive object that creates most of what we experience as gravity in everyday life. Time runs slower near a massive object than far from it. Objects fall not because they are pulled, but because they are following the straightest possible path through curved space-time. And because of the time curvature, the straightest path leads toward the mass. Now, quantum mechanics. Quantum mechanics is the theory of how reality works at the smaller scales: atoms, electrons, photons of light, the particles that make up all matter and all energy. Its rules are strange by the standards of everyday experience, but they have been confirmed by every experiment ever devised to test them. The central strangeness is this: at the quantum level, particles do not have definite properties until those properties are measured, and the electron does not have a definite spin, up or down, until you measure it. Before measurement, it exists in a superposition of both states simultaneously. When you measure it, the superposition collapses to one definite value. The wave function, the mathematical object that describes the electron's quantum state, evolves according to a precise equation, the Schrödinger equation, until the moment of measurement. Imagine a coin spinning in the air. While it spins, you cannot say it is heads or tails. It is genuinely both. When it lands and you look, it is one or the other. Quantum superposition is like this, except that the spinning coin description is not just our ignorance of which way it will land. The coin really is both, in a physical sense, until it lands. The evidence for this is not philosophical but experimental. Quantum particles in superposition interfere with themselves, producing patterns that only make sense if both possibilities were real and simultaneously present before measurement. The feature of quantum mechanics that makes it collide with black holes is unitarity. Unitarity is the mathematical property that says quantum states evolve in a reversible way. Given the final state, you can always, in principle, reconstruct the initial state. Information is conserved. The evolution of the universe at the quantum level is like a perfectly structured code. Every output contains, in scrambled form, the complete description of the input. General relativity, however, was constructed without any reference to quantum mechanics. Einstein's equations describe smooth, continuous space-time. They have no concept of quantum states, of superposition, of unitarity. They work magnificently at the scale of planets and stars and galaxies. They fail at the scale of atoms and particles, and at a black hole, where enormous mass is compressed to scales smaller than an atom. Both theories apply simultaneously, and they contradict each other. This is not like two maps disagreeing on the exact location of a border town. It is more like two maps of the same city, one drawn for cars and one drawn for underground trains. that are mutually contradictory in a way that makes it impossible to say which one describes the real layout of the city's streets. Neither map is wrong on its own terms, but they cannot both be right about the same city. Either one of them is wrong in some way it doesn't know about, or the city has a structure that neither map can represent, and we need a completely different kind of map. That different kind of map is what physicists call a quantum theory of gravity, a theory that describes space-time itself in quantum mechanical terms. We do not have this theory. Despite decades of effort by thousands of physicists, we do not have a complete, experimentally verified quantum theory of gravity. String theory is a candidate. Loop quantum gravity is a candidate. There are others. None has been confirmed. None has been ruled out. This is the deepest open problem in fundamental physics. Black holes are where this problem becomes urgent, because it is inside a black hole that both gravity, at its most extreme, and quantum mechanics, in its implications for information, are simultaneously essential. The black hole is not just an exotic astrophysical object. It is a laboratory for the deepest physics, one we cannot enter, cannot observe from inside, and can only probe through mathematical inference and theoretical argument. One more piece of background is essential: the holographic principle. In 1997, Juan Maldacena at Harvard University published what is now one of the most cited papers in the history of theoretical physics. He showed, in a specific mathematical framework, not as a vague analogy, that a certain theory of gravity in 3 dimensions of space is exactly equivalent to a quantum theory without gravity in 2 dimensions. The 3-dimensional world, including all its gravitational dynamics, is perfectly encoded in a 2-dimensional surface. It is a hologram in the strict mathematical sense. The boundary contains all the information of the interior. This result, the ADA/CFT correspondence, does not describe our universe directly. The specific geometries involved differ from our spacetime, but it provides a working proof of concept for a radical idea that the 3-dimensional, gravitational, curved spacetime universe we inhabit may be, in some precise mathematical sense, a projection of information encoded on a lower dimensional surface. The implications of this, for what lies beyond the black hole horizon, for what space itself is made of, we will explore in the sections that follow. For 20 years after Hawking announced his radiation in 1975, the information paradox was largely treated as a curiosity, an interesting theoretical puzzle that would presumably be solved once someone figured out the quantum corrections to general relativity near the horizon. Then, in 1996, 2 physicists independently made a calculation that changed everything. Andrew Strominger and Kamran Vafa at Harvard University chose a very specific type of black hole, one that can be described in string theory with great mathematical precision, and calculated its entropy using quantum mechanical methods by actually counting the number of quantum states available to the string theory objects that compose it. They got the Bekenstein-Hawking formula exactly, not approximately, exactly. This was not just impressive mathematics, it was a declaration. If you can count the quantum states of a black hole, if you can account for the entropy by literally listing the possible internal configurations, then the information is there. The information is real. The black hole has a quantum description, and if the black hole has a quantum description, then the information that falls in must, in principle, come out when it evaporates, encoded in the Hawking radiation, however scrambled, however difficult to decode, but this immediately deepened the problem rather than resolving it. How does the information get out? General relativity says the infalling information goes toward the singularity. Quantum mechanics says the outgoing Hawking radiation is generated just outside the horizon, where the infalling material has not yet arrived. The 2 regions are causally disconnected. Information cannot cross from one to the other without violating the causal structure of spacetime. Leonard Susskind at Stanford had been arguing for years, loudly, persistently, often against the opinions of the majority, that information must survive. His position was not popular. Stephen Hawking himself believed information was destroyed and said so publicly. But in 1993, Susskind and collaborators proposed something radical: black hole complementarity. The idea was this: Alice, falling into a black hole, experiences nothing unusual at the horizon and carries her information inward. Bob, watching from outside, sees that information encoded in the Hawking radiation and eventually retrieved. Both descriptions are correct, but they cannot both be verified by a single observer, because no single observer can be both inside and outside the horizon simultaneously. Quantum mechanics, Susskind argued, only requires that observations made by a single observer are consistent. Different observers can have contradictory descriptions, as long as no single observer can verify both. This is Revelation 1, the first ground shift. The rules of physics, which we assumed were universal, which we assumed described the same reality for every observer, may be perspective-dependent in a way that goes beyond anything we have encountered before. Two observers can disagree not just on measurements, but on the fundamental question of whether a piece of information exists. The ground has just moved beneath your understanding of what it means for something to be real. Black hole complementarity was clever, but it had a problem. Susskind and his collaborators assumed that quantum mechanics would prevent any single observer from collecting enough information to create a paradox. In 2012, the AMPS paper, The Firewall Argument, showed this assumption was wrong. A sufficiently patient observer could, in principle, collect enough Hawking radiation to demonstrate that the same quantum bit was in two places at once inside the black hole, with the infalling matter and outside the black hole encoded in the already emitted radiation. This would be a violation not of some obscure technical rule, but of the most fundamental prohibition in quantum mechanics, the no-cloning theorem, which says that a quantum state cannot be copied. You cannot have the same information inside and outside. One of the two has to be wrong. This is the point at which Juan Maldacena and Leonard Susskind proposed their extraordinary connection, ER equals EPR. In their 2013 paper, they argued that the apparent contradiction dissolves if you accept something remarkable. The entanglement between the Hawking radiation outside the black hole and the interior of the black hole is not just a correlation, it is a geometric connection, a wormhole. The particle outside and the particle inside are connected by a tube through space-time, not a traversable wormhole, not a shortcut you can travel through, but a genuine geometric link that makes them not just correlated but spatially connected through a deeper structure of space-time. Imagine you have two gloves separated by an ocean. You pack one glove in a box in New York without looking at it and ship the other to London. When someone in London opens their box and finds a left glove, they instantly know the box in New York contains a right glove. That is classical correlation, nothing strange. Now imagine that the two gloves are quantumly entangled. They are in a superposition of left-right and right-left until measured. When measured, the correlation is instantaneous regardless of distance. Einstein called this spooky. Maldacena and Susskind are saying the spookiness is actually a tunnel. The two gloves are connected by a thread of space-time too small to travel through, but real and geometric. What we call entanglement is what a wormhole looks like when viewed by quantum mechanics. The implication, and this is Revelation 2 and is Protagonist, is that space-time is made of entanglement, not metaphorically, the connectivity of space, the fact that two regions of space are adjacent, that they can influence each other, that light can travel from one to the other, emerges from the entanglement of the quantum fields that permeate those regions. If entanglement is destroyed, the space between the regions becomes disconnected. Space-time tears. Mark van Ramsdonk at the University of British Columbia made this explicit in a celebrated 2010 paper, showing that in the ADSA/CFT framework, reducing entanglement between two halves of a quantum system corresponds to the space-time connecting them becoming a thin tube and eventually breaking apart entirely. Entanglement is the stitching that holds space-time together. This means that the black hole information paradox is not just about information, it is about the origin of space itself, and any theory that resolves the paradox is not just fixing a technical problem in black hole physics. It is explaining why space has the property of being connected at all. In 2019, a development came from an unexpected direction. Physicists working on the information paradox, using the tools of ADS/CFT, the holographic correspondence, found a new way to calculate the entropy of the Hawking radiation emitted by an evaporating black hole, and the calculation gave a result that had been hoped for but never proven. The result was the Page curve. In 1993, Don Page at the University of Alberta had argued, using general quantum mechanical reasoning, that if a black hole evaporates while preserving information, the entropy of the Hawking radiation should follow a specific pattern. In the early stages of evaporation, the radiation's entropy should increase as more and more information is encoded in it. But at a specific moment, the page time, roughly the halfway point of the black hole's lifetime, the entropy should start decreasing as the later radiation purifies the earlier radiation, decoding the information. Eventually, when the black hole has fully evaporated, the entropy of the radiation should return to zero. All the information is out, perfectly encoded in the correlations among the Hawking photons. If Hawking was right, if information is destroyed, the entropy would increase monotonically until the black hole disappears and then drop abruptly to zero. This is not what quantum mechanics predicts. This would be the information paradox in its starkest form. For 25 years after Page's paper, no one could calculate which curve was correct from first principles. No one could derive the Page curve from the microscopic physics of the black hole. Then, in 2019, multiple groups, Ahmed Almheri, Netta Engelhardt, Henry Maxfield, and Jeff Pennington, working independently in overlapping teams, derived the Page curve from a direct calculation in the gravitational theory. The key ingredient that made the calculation work was something called an island, a region inside the black hole that contributes to the entropy calculation of the Hawking radiation outside the black hole. Not through any signal crossing the horizon, not through any causal channel, but through a quantum gravitational effect in which the interior region is effectively included in the entropy calculation of the exterior. What this means, and this is revelation 3, and it is the most extraordinary of the three, is that the interior of the black hole is not fully separate from the outside. The information inside the black hole is, in some precise quantum gravitational sense, already on the outside, encoded in the entanglement structure of the Hawking radiation. The horizon is not a complete barrier. It is porous in a way that space-time, by itself, does not reveal. Quantum gravity makes the interior and exterior of a black hole not two separate regions, but two descriptions of the same region, related by a duality that has no classical analog. The firewall is resolved, not by showing it doesn't exist, but by showing that the question of what exists on either side of the horizon is not as simple as inside and outside. The geometry of space-time is not the fundamental layer of reality. It is an emergent description, and what it is emergent from, the deepest structure that space-time arises from, is quantum information. The universe at its deepest level may not be made of space and time and matter. It may be made of information, and what we call space is the geometry of how that information is organized. The story you have been hearing is not speculation. Every major claim in this documentary connects to specific scientists, specific calculations, specific papers that have survived the rigorous process of peer review and response. Let us bring those names and findings into focus. Stephen Hawking, University of Cambridge, published Particle Creation by Black Holes in Communications in Mathematical Physics in 1975. This was the paper that derived Hawking radiation, the thermal radiation emitted by black holes as a consequence of quantum field theory in curved space-time. Hawking's conclusion in this paper, that the radiation carries no information about the internal state of the black hole, was the opening statement of the information paradox. For the next 3 decades, Hawking argued that information is genuinely destroyed, and that quantum mechanics would have to be modified to accommodate this. In 2004, at the GR17 conference in Dublin, Hawking publicly conceded that he had been wrong, that information is preserved. He based his concession on the AD-CFT correspondence. He arrived at the conference in his wheelchair, flanked by reporters, and delivered a talk that the scientific community received with a mixture of respect and careful skepticism. Some found his argument for information preservation unconvincing in its specifics, even if they agreed with the conclusion. It was one of the most publicly dramatic reversals in the history of modern physics. Jacob Bekenstein, then a graduate student at Princeton University working with John Wheeler, published Black Holes and Entropy in Physical Review D in 1973. Bekenstein's insight, that a black hole's entropy is proportional to the area of its event horizon, was initially dismissed by Hawking, who pointed out that if a black hole has entropy, it must also have temperature, and if it has temperature, it must radiate, which no one at the time believed. When Hawking subsequently showed that black holes do indeed radiate thermally, he simultaneously confirmed Bekenstein's formula and created the information paradox. The Bekenstein-Hawking entropy formula, S equals A4, in units where Newton's constant, Planck's constant, and the speed of light are all set to 1, remains one of the most profound and mysterious equations in physics. Its derivation from the microscopic theory of string theory by Strominger and Waffer in 1996 was one of the great confirmations of that theory, though it remains a confirmation in a special case, not the full story. Juan Maldacena, Institute for Advanced Study, Princeton, published The Large N-Limit of Superconformal Field Theories and Supergravity in the International Journal of Theoretical Physics in 1998. This is the ADES-CFT paper, commonly called the most cited paper in physics, with over 20,000 citations as of 2024. The correspondence it establishes between a gravitational theory in an anti-de Sitter spacetime and the quantum field theory on its boundary has become the primary mathematical tool for studying black hole physics in a theoretically controlled way. Maldacena's work provides the setting in which the page curve derivation of 2019 was made possible, and in which the ER equals EPR proposal was formulated. Ahmed Al-Naheri, now at New York University, Abu Dhabi, was the lead author of both the 2012 AMPS firewall paper, with Donald Maroff, Joseph Polchinski, and James Sully, all at UCSB, and the 2019 Island formula papers that derived the page curve. The firewall paper, Black Holes, Complementarity or Firewalls, published in the Journal of High Energy Physics in 2013, is widely credited with reopening the information paradox after many in the community thought it had been resolved by Susskind's complementarity argument. The Island formula papers, published in RxCiv in 2019 and subsequently in Journal of High Energy Physics in 2020, represent the most significant technical progress on the information paradox in 2 decades. Netta Engelhardt, Massachusetts Institute of Technology, was a co-discoverer of the Island formula. Her work with Al-Naheri, Maxfield, and Pennington in 2019 showed, for the first time, how a quantum gravitational calculation could reproduce the page curve, the behavior expected if information is preserved. The key technical innovation was the identification of quantum extremal surfaces, generalizations of the classical surfaces used in the Bekenstein-Hawking entropy formula, which include quantum corrections and can extend into the interior of the black hole. Jeff Pennington, University of California, Berkeley, independently derived similar results simultaneously, approaching the problem from the perspective of the total entropy of the radiation region. His paper and Al-Naheri et al.'s paper were posted to RxCiv within days of each other in September 2019. In one of the more striking cases of simultaneous independent discovery in recent theoretical physics, Don Page, University of Alberta, published Information in Black Hole Radiation in Physical Review Letters in 1993. Page's curve, the specific shape that the entropy of the Hawking radiation should follow if information is preserved, had been the target of the derivation attempts for 25 years before it was finally reproduced in 2019. Page himself has noted the mixture of satisfaction and caution appropriate to the 2019 result, satisfaction that the calculation finally works. Caution because the ADES-CFT setting in which it works is not identical to our universe, and the extension of the result to realistic black holes in a cosmological setting remains an open problem. Mark van Ramstonk, University of British Columbia, published Building Up Spacetime with Quantum Entanglement in General Relativity and Gravitation in 2010. His paper demonstrated, within the ADES/CFT framework, that the geometry of spacetime emerges from the pattern of entanglement in the boundary quantum system. Reducing entanglement between two halves of the boundary quantum system corresponds to the bulk spacetime geometry, connecting the two regions becoming increasingly thin and eventually disconnecting. This result is foundational to the interpretation that spacetime is built from quantum information. What does it mean if spacetime is made of information? Start close, start within the field. For fundamental physics, for the project of understanding the deepest rules of the universe. The implication is this: gravity is not fundamental. Spacetime is not the bottom of the stack. The smooth, curved, four-dimensional spacetime that general relativity describes, the spacetime in which you and I and every galaxy live, is an emergent phenomenon, like temperature. Temperature is not a fundamental property of matter. It is what emerges when you average over the motion of billions of molecules. Individual molecules do not have temperature. Temperature is the large-scale, coarse-grained description of something that, at the microscopic level, is pure kinetic energy. In the same way, space-time may be what you see when you coarse-grain over quantum information. Individual quantum bits do not live in space-time. Space-time is what you get when you have enough entangled quantum bits organized in the right way and you zoom out far enough. Consider the screen you are watching this on. At the pixel level, it is a grid of tiny squares, each with a specific color value, a number. From far enough away, those numbers describe a landscape, a face, a galaxy. The landscape is not in the screen. The screen contains only numbers. The landscape is what emerges when the numbers are correctly organized and you step back. Space-time may be, in this precise and technical sense, the landscape you see when you step back from quantum information organized at a scale below our ability to probe directly. Now, step outward. What does this mean for the fields that depend on space-time being fundamental? Cosmology, the study of the origin and large-scale structure of the universe, depends on general relativity at its foundations. The Big Bang is not an explosion in space. It is the beginning of space-time itself, or at least the earliest moment accessible to our current physics. If space-time is emergent, if it arises from quantum information, then the question, what happened before the Big Bang, is no longer unanswerable on principle. It becomes a question about the quantum informational substrate from which space-time emerged. What was the state of the quantum information before the space-time that we inhabit crystallized out of it? We do not know. But the question is now meaningful in a way it was not before. The problem of dark energy, the mysterious energy density of empty space that is causing the universe's expansion to accelerate, may be connected to the same deep structure. If the vacuum of space has an energy because empty space is populated by entangled quantum fields, and if the geometry of space-time arises from the entanglement of those fields, then the energy of the vacuum and the geometry of space-time are not independent quantities. Changing the entanglement changes the geometry. This is, at present, a direction of research rather than a solved problem, but it connects the largest scale mystery in cosmology to the microscopic structure of space-time. Now step all the way out. What does it mean for you? You are a physical system. Your body, your brain, your thoughts, your memories, all of it is, at the most fundamental level, a pattern of quantum information encoded in the physical matter that constitutes you. If information is the most fundamental thing in the universe, if space-time arises from information, if matter arises from information, if the separation between here and there is a consequence of the organization of information, then the question of what you are is not merely a biological or psychological question. It is a question about the deep structure of reality itself. John Archibald Wheeler, the physicist who coined the term black hole, who mentored a generation of theoretical physicists including Kip Thorne and Jacob Bekenstein, spent the last decades of his life pursuing an idea he called it from bit. The idea was this: every particle, every field, every force, every dimension of space and time, every it in the universe derives its existence from answers to yes or no questions, from binary choices, from bits of information. The universe is not made of matter in this picture, it is made of information. Matter is what information looks like when you are inside it. Wheeler never made this rigorous. It was a late career intuition, a direction rather than a theorem. But the developments in black hole physics over the past 30 years, the Bekenstein entropy, the holographic principle, ADS/CFT, the island formula, have moved it from philosophical speculation toward what looks, tentatively, like a research program with genuine mathematical content. If you are a pattern of information, then the question of what happens to the information in a black hole, does it survive? Is it somewhere? Has a faint, distant, terrifying echo in the question of what happens to the information that constitutes you when you die. This is not science. This is the edge where science meets the oldest human questions, and it would be dishonest to pretend the echo does not exist. What we can say with confidence is this: the universe keeps accounts. The total quantum information in a closed system does not decrease. It is scrambled, dispersed, made practically irretrievable. But it is not destroyed. The implication, if taken seriously, is that the universe contains a complete record of everything that has ever occurred at the level of quantum states. The past is not gone, it's encrypted, and black holes may be the most extreme encrypting machines the universe possesses. No single theory has resolved the black hole information paradox. The 2019 Island formula derivation is significant progress, but it is not a final answer. It works within a specific framework, under specific assumptions, and its extension to the real universe is not complete. In the absence of a complete theory, multiple competing proposals remain alive. Each has genuine strengths. Each has genuine problems. None has won. This is not a weakness. This is where the physics actually lives. The remnant hypothesis proposes that when a black hole evaporates, it does not disappear completely. Instead, it leaves a stable, Planck mass remnant, a microscopic object with a mass of approximately 10 micrograms, governed entirely by quantum gravity. All the information that fell into the black hole is stored in this remnant. The information paradox is resolved because the information never leaves in the Hawking radiation. It simply waits in the remnant indefinitely. The proponents of this view include several researchers in the quantum gravity community, though it has fallen out of favor in recent years. The strongest evidence for remnants is negative. It avoids the paradox cleanly, without requiring any exotic modification of either quantum mechanics or general relativity in the regime where they are well tested. The most serious weakness is also entropy. If a Planck mass remnant contains all the information of a black hole that might have swallowed a galaxy, it must have an effectively infinite number of possible internal states. This creates severe problems for quantum field theory. It means there should be an infinite number of virtual remnants contributing to ordinary physical processes, producing corrections to measurable quantities that should be enormous and are not observed. A remnant storing unlimited information in a fixed size package is a bit like a filing cabinet the size of a shoebox that contains, somehow, all the records of every human being who has ever lived. Not just the names, the complete quantum state of each one. The shoebox does not bulge. The files are all there. The contradiction with everything else we know about physical storage makes most physicists uneasy with this proposal. This is the position that most working physicists currently lean toward. Not because it is proven, but because it is the most consistent with unitarity and the holographic principle. The claim is that Hawking's original calculation was an approximation, valid for large black holes in the early stages of evaporation, but failing for smaller black holes and near-complete evaporation. The corrections to Hawking's calculation, when properly accounted for, encode the infalling information in subtle correlations among the emitted photons. This is what the page curve derivation of 2019 suggests. The information does come out. It is not destroyed, but it comes out in a form so scrambled, so deeply encoded in correlations among billions of photons emitted over millions of years, that decoding it is practically impossible. Theoretically, given a perfect quantum computer and knowledge of every Hawking photon ever emitted, you could reconstruct the interior as the black hole. Practically, you cannot. The strongest evidence for this position is the page curve derivation itself, and the broader consistency of AdS/CFT. The most serious weakness is that the mechanism by which the information gets out, how exactly quantum gravity modifies Hawking's calculation to allow information to escape, is not understood in detail. The Island formula tells you what the entropy curve looks like. It does not give a clear physical picture of how the information travels from the interior to the exterior. The firewall proposal from Almheri, Maroff, Polchinski and Sully is not so much an alternative resolution as an alternative description of the problem. If information must survive and quantum mechanics must work correctly, then an infalling observer does not experience a smooth horizon. Instead, they encounter a wall of high-energy radiation at the horizon, a firewall, that converts all infalling matter into Hawking radiation before it crosses the boundary. The firewall resolves the information paradox by preventing anything from actually crossing the horizon in a coherent quantum state. The information never gets in, so it does not need to get out. The proponents argue that this is the correct implication of taking both unitarity and quantum field theory seriously. The weakness is the equivalence principle, the foundational postulate of general relativity that a free-falling observer cannot locally distinguish their situation from being in empty flat spacetime. The firewall explicitly violates this. A firewall at the horizon of a large black hole, where the local curvature is mild and every local measurement should give flat space results, is a direct contradiction with Einstein's foundational assumption. Accepting the firewall means accepting that general relativity fails, not at the singularity where we might expect it, but at the horizon where the local physics should be perfectly tame. String theory. The proposal that fundamental particles are not point-like objects but one-dimensional vibrating strings offers a different picture of a black hole's interior. In the fuzzball proposal, developed primarily by Samir Mathur at Ohio State University, a black hole has no interior at all in the conventional sense. The classical description, empty space-time inside the horizon, singularity at the center, is replaced by a dense, stringy structure that fills the entire region within the Schwarzschild radius. The horizon is not an empty boundary. It is the edge of the fuzzball, a physical surface made of excited string states. In this picture, information is never trapped inside a classical horizon because there is no classical horizon. The Hawking radiation is emitted by the surface of the fuzzball, and it carries the information of the internal string state. The paradox dissolves because the object never had an interior in the first place. The strongest evidence for fuzzballs is that, in string theory, they can be constructed explicitly for certain classes of black holes, and their entropy can be derived. The most serious weakness is that fuzzballs require string theory to be the correct theory of quantum gravity, a hypothesis for which we have no direct experimental confirmation. Additionally, for a large black hole, the fuzzball surface should be indistinguishable from a classical horizon by any local measurement, which makes it unclear how the fuzzball avoids the problems that motivated the firewall proposal. Susskind's original complementarity proposal has been substantially revised in recent years, incorporating the ER equals EPR idea and the island formula results. In its current form, complementarity proposes that the interior and exterior of a black hole are not two separate regions of spacetime, but two descriptions of the same quantum system. The interior is not behind the horizon in any absolute sense. It is a decoded description of the same quantum information that constitutes the exterior. In this view, the question, what happens to information inside a black hole, has the same structure as asking what happens to a letter written on the back of a mirror. It is right there, if you know how to read it. The information is in the correlations of the Hawking radiation. The interior spacetime is the holographic dual of those correlations. There is no separate interior. There is only the quantum information and two complementary ways of describing it. This is the position that has the most support in the theoretical physics community at present. Its weakness is that the holographic duality it depends on is well established in anti-de Sitter space, a negatively curved spacetime that differs from our own flat or slightly positively curved universe. Whether the resolution extends to cosmological black holes in de Sitter space is an open and actively contested question. There is a moment in the history of every field of science when the questions it asks stop being questions about the field and become questions about the questioner. When physics stopped asking, what are the planets made of, and started asking, what is space made of, it crossed a line from the study of nature into something closer to metaphysics, using mathematics instead of language. The information paradox has crossed that line. The questions it raises are not questions that can be answered by building a better telescope or designing a cleverer experiment. They are questions about the nature of information, the nature of reality, and the nature of the observer. They are questions that science is only beginning to have the vocabulary to ask. The philosopher and mathematician Gottfried Wilhelm Leibniz asked, in 1714, "Why is there something rather than nothing?" It is the oldest and in some ways the only question in metaphysics. Wheeler's it from bit, the proposal that information is the fundamental substrate of reality, does not answer Leibniz's question. But it transforms it. If the universe is made of information, then the question, why does the universe exist, becomes why does this particular information exist? And that question has a structure that, unlike Leibniz's original formulation, might be accessible to physics. Consider a library. Not a real library, a perfect Borgesian library containing every possible book, every sequence of letters that could fill a given number of pages, including all the books ever written, and all the books that could ever be written, and all the books that are pure gibberish. Such a library contains, somewhere, a perfect description of every possible universe. The question is not whether your universe is described in the library, it is. The question is, why does your universe exist, rather than merely being described? The library metaphor taken seriously leads you immediately to the edge of what physics can say and into the territory that only philosophy has so far dared to occupy. The physicist and mathematician Roger Penrose, who shared the 2020 Nobel Prize in Physics for his work on black hole singularities, has spent much of his career arguing that quantum mechanics, general relativity, and consciousness are all connected through a mechanism involving quantum gravity. His proposal, orchestrated objective reduction, developed with anesthesiologist Stuart Hameroff, is contested and not mainstream, but the instinct behind it, that the physics of quantum gravity is relevant not just to cosmology and particle physics, but to the nature of mind, is shared by a broader community than is sometimes acknowledged. Penrose has written that the universe's low-entropy beginning, the extraordinarily ordered state from which the Big Bang emerged, is itself a profound mystery that current physics cannot explain. The initial conditions of the universe are, in Penrose's phrase, absurdly special. If the universe is made of information, and if the initial conditions were an extraordinarily precise and ordered arrangement of that information, then the question of what set those initial conditions is the same as the question of what determined the initial quantum state of all the information in existence. That is the question at the end of the chain. It does not have a physical answer. It might not have an answer at all. The physicist Carlo Rovelli, one of the founders of loop quantum gravity, writes in his book, 7 Brief Lessons on Physics, a book that has been read by millions of people who would never describe themselves as interested in physics, that the nature of time is perhaps the greatest remaining mystery. In loop quantum gravity, time itself is not fundamental. It emerges from the quantum gravitational dynamics, the way temperature emerges from molecular motion. There is no time at the Planck scale. Time is what it looks like when you coarse-grain over quantum gravitational states. If time is emergent, then the question, what happened before the Big Bang, is not just unanswerable, it is ill-formed. The word before requires time. If time did not exist before the Big Bang, before is as meaningless as north of the North Pole. And yet the information that the universe contains, the quantum information that is currently organized into galaxies, stars, planets, and people, had to come from somewhere, or did it? If information is fundamental, and if the universe is simply the information that there is, then perhaps the question, where did the information come from, is as ill-formed as north of the North Pole. The universe is not a consequence, it is the ground. You have watched this entire documentary, you have sat with Schwarzschild doing calculations in the trenches. You have stood in the Chilean desert with Cristina Romero and looked up. You have followed the argument from Hawking's 1975 calculation to the firewall, to the island formula, to the proposal that space-time is stitched from entanglement. And you are now, perhaps, doing what every physicist who has worked on these problems eventually does. You are sitting with a question that you cannot fully hold in your mind, feeling simultaneously that it is almost within reach and permanently beyond grasp. That feeling is not a failure of understanding. It is the honest intellectual response to a genuinely open question at the edge of human knowledge. The physicist Richard Feynman, who won the Nobel Prize for Quantum Electrodynamics and who was one of the most insightful scientists of the 20th century, said that he had learned to live with not knowing, because not knowing was the condition of the scientist, and that it was a far more interesting condition than false certainty. The deepest questions in physics are not embarrassments. They are the proof that the universe has more structure than we have yet been able to see. Here is where we have arrived, not at an answer, but at a better question, a more precise question, a question whose contours we can trace now that we could not at the beginning. We began with the impossible statement, everything that has ever fallen into a black hole still exists. We have now earned the right to understand why that statement might be true, and what it cost the universe to make it true. If information is conserved, if the universe truly keeps accounts, then the survival of information inside a black hole is not a matter of it being stored in some hidden chamber behind the horizon, waiting to be retrieved. The interior is not a separate place. In the deepest available framework we have, the holographic correspondence, the island formula, the ER equals EPR connection, the interior is a description. It is the decoded version of the correlations among Hawking photons emitted over the entire lifetime of the black hole. The black hole does not hide information. It is information. a spectacularly elaborate, maximally scrambled encoding of every quantum state that ever fell into it. What this means, and this is the thing to carry away from this documentary, is that the boundary between inside and outside, between here and there, between the accessible and the inaccessible, is not a fixed feature of reality. It is a consequence of how information is organized. Change the organization of the information and you change the geometry. Change the geometry and you change which regions of space are accessible, which events are causally connected, which locations are inside and which are outside. You have probably thought of space as the stage on which events happen, the empty container in which things exist and move and interact. That picture is not wrong for most purposes. But at the deepest level, it may be backward. Space is not the container. Space is the pattern. Spacetime is the shape that information takes when it is organized in the particular way that our universe organizes it. Different organizations produce different geometries, different connectivities, different causal structures. The black hole, in this light, is not a hole in space. It is a region where the information is organized in such a way that the geometry isolates it, where the pattern has folded back on itself in a configuration that, from our position in the low curvature exterior, looks like a one-way door. But the information is never truly isolated. It is always connected to the rest through entanglement, through quantum gravity, through the subtle long-range correlations that the island formula reveals. The horizon is a feature of the geometry, not of the information. And the geometry, we now suspect, is the surface. The information is the depth. But here is what we still do not know. We do not know the mechanism. We can prove, within the ADS/CFT framework, that information must be conserved. We can derive the